Hi everybody, today we're going to focus on series circuits, and you might have heard about series circuits in your grade 9 electricity unit. If you don't remember anything, or if you do, that's great, but we're just going to take a little further look into it today. So on page 716 is an explanation of series circuits, and you can take a look at that if you want some further explanation. So on page 716, there's this picture of a ski hill. So as skiers go around a ski circuit, the lift raises them up to the top of the hill, right? So when you're at the top of the hill in a series circuit, it consists of 3 downhill runs, indicated here by the different colors, so green, blue, and red, and one after the other with level paths connecting the runs. It's a really good analogy of a series circuit. So since there's only one route down, right? See how there's only one way that skiers can travel down the route. The number of skiers going down each run would have to be the same. So if there's 3 skiers going down here, there has to be 3 skiers that will pass the blue, and then 3 go down the red, because there's only one way down the hill. So the total height of the 3 runs, so the total height, so the height of this, and the height of this, and the height of this, has to equal the height of the entire hill, right? Otherwise they wouldn't get down again. So the combined height of the 3 runs must equal the height of the hill. So this is the same as in a series circuit. And we know this is all related to gravitational potential energy. So that's what this is showing us. And that's the exact same as our volts, our electric potential difference. It's the same thing. Okay, so now over here, this is a series circuit. Okay, so a series circuit consists of loads, which is resistances, right? So these things that are, and it's connected in series. So to me, series just means that resistors come one after the other and that it's along the same line. Okay, so the current that leaves here, the current that leaves this end of the battery only has one path to follow. So just as skiers in the previous analogy must all ski down each run in sequence, all of the current that leaves here must pass through each of these loads. So the same amount of current that comes through here has to pass through all of these loads, all of these resistances. So an ammeter, which measures current, could be connected anywhere along here, and it would be the same amount of current. So each reading would be the same, right? So the current here, so say it's 2 amperes, has to be the same at this resistance, so it has to be 2 amperes, and then all the way to current 3, like here at resistor 3, has to be the same. It would be the same as 2 amperes here. So here's our little formula. So the current of the source, S means the source, which would be the battery, has to be the same. So if this is 2 amperes, it's going to be 2 amperes of the source, 2 amperes the current at 1, and the same, so forth. Okay, so the current is always the same. But then also, just as the total height of the hill, right? So the total height of all of this, it must be shared over the 3 runs. The potential difference, so the voltage must be shared over all 3 loads. So it has to be shared. So if we look at this equation for voltage, the voltage of the source is equal to the voltage of the summation of all the voltages at the resistors. So V1 plus V2 plus V3 has to equal the voltage of the source. So if we look here, if the voltage of the source is 6 volts, at each of these resistors, the voltage has to be added to equal 6 volts. So at each of these, it would have to be 2, right? So it would be 2 volts, 2 volts, 2 volts, because 2 plus 2 plus 2 equals 6 volts. Okay? So equivalent resistance in a series circuit looks like this. So equivalent resistance is Req. So the total of potential differences, so voltages, across each individual load, R, must equal the potential difference across the battery, the source. So all of the current that leaves the battery must pass through each load. So these are the 2 equations that we've seen on the last slide. So the voltage of the source is V1 plus V2 and so on. But then for current, the current of the source equals the current at I1, I2, I3, so it's all the same. So if we then put that into Ohm's law, so V equals IR, you'll get this equation. And what you should notice is because the current is the same at all loads, we can cross that out. So the equivalent resistance equals R1, R2, R3, and the summation of them. So adding it all up. So equivalent resistance of loads in a series circuit is using this equation. Okay, so you'll use Vs, right, in Ohm's law, so it'll look like Vs equals Is Req. And you'll use that and rearrange that to find and to solve for those unknowns. Okay, so do this homework or these questions, so 27 to 31. Give it your best shot. Ask me any questions. Join the Google Meet. Email me. Have a good day.